Hello everybody, welcome back to ATM 5, Our Changing Atmosphere. In today's lecture we'll be learning about the science of global warming, one of the most obvious effects related to climate change. With our knowledge of energy in the Earth system in hand, we can now examine what effect our emissions have had on energy in the Earth system. In this section we'll be defining representative concentration pathways, or RCPs, and shared socioeconomic pathways, or SSPs. We'll also be answering these questions. What is the Intergovernmental Panel on Climate Change? Are human activities responsible for warming the Earth? What are the major drivers of anthropogenic climate change? And how do we experience climate change? Before proceeding on the science of global warming, I want to dedicate a brief aside to the Intergovernmental Panel on Climate Change, or more succinctly, the IPCC. The IPCC is an international organization under the United Nations tasked with compiling international research on the subject of climate change caused by human activity. Although it does not generate scientific research itself, it is tasked with bringing together the current state of the science in a series of regular assessment reports. As mentioned earlier in this class, 5 complete assessment reports have been published as of 2020, with the 6th assessment report expected to be completed by 2022. These reports are one of the most important sources of research on the study of climate change. The IPCC sits under the World Meteorological Organization and the United Nations Environmental Program, and consists of a plenary, bureau, and executive committee. The plenary consists of 195 member governments, each indicating one representative of their organization. The IPCC Bureau is an elected group of 34 members that provides guidance to the panel on scientific and technical aspects of its work, consisting of the IPCC chair, vice chairs, co-chairs, and vice chairs of the 3 working groups, as well as co-chairs on the task force on national greenhouse gas inventories. Above the Bureau is the executive, consisting of the most senior personnel in the IPCC. The IPCC further consists of 3 working groups which tackle the science of climate change. Working Group 1, which focuses on the physical science basis, a principal focus of this course. Working Group 2, which focuses on the impacts of climate change, how to adapt to a changing climate, and understanding global vulnerabilities of climate change. And Working Group 3, which focuses on mitigating or fighting climate change. Each of these working groups has a large number of authors, contributors, and reviewers that volunteer their time to compile the latest science as part of each working group. The semi-regular assessment reports then consist primarily of 4 publications, 3 reports from each of the working groups, and a 4th synthesis report. The order of publication is consistent with the order of the working groups, and the synthesis report is always published last. The framework underlying the IPCC is depicted here. Their work bridges Earth systems and human systems. In the context of the Earth system, the focus is on the effects of climate change, including extreme events, sea level rise, temperature change, or global warming, and precipitation change. Climate change is of course driven by greenhouse gases and aerosols, and an understanding of climate change is necessary for assessing impacts and vulnerability, including ecosystems, food security, water resources, settlements and society, and human health. But continued global socioeconomic development is the driving factor behind these emissions, and is of course impacted by modifications to the climate system induced by climate change. Dealing with climate change inevitably requires a 2-pronged strategy: adaptation and mitigation. The former, adaptation, means adapting to the changes brought on by climate change and building resilience in society. The latter, mitigation, means reducing the damage from climate change. These 2 topics will be explored in detail later in this class. The 5th assessment report publications are readily available online. To read the full report and synthesis report, you can follow the link here, or simply Google 5th assessment report. To follow the status on the 6th assessment report, follow the link at the bottom of this slide, or simply Google 6th assessment report. Since the IPCC first began publication of their assessment reports, we've gained confidence in the reality of human influence on global climate. In the 2nd assessment report in 1995, the consensus was that the balance of evidence suggests a discernible human influence on global climate. In 2001, this confidence had grown, and the IPCC had made the statement that there is new and stronger evidence that most of the warming observed over the next 50 years is attributable to human activities. In 2007, in the 4th assessment report, The consensus was that most of the observed increase in globally average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. Here, very likely is a term that comes from meta-analysis, which is the science of science, how to combine results from multiple studies to draw conclusions with greater confidence. Quantitatively, it means that there is above 90% confidence in the strength of this statement, drawn from the weight of evidence that suggests no other known factors could be causing warming of the character observed. As of the fifth assessment report, the consensus has grown even stronger. Now, the science shows that with 95% certainty, human activity is the dominant cause of observed warming since the mid-20th century. The report confirms that warming in the climate system is unequivocal, with many of the observed changes unprecedented over decades to millennia. Warming in the atmosphere and the ocean, diminishing snow and ice, rising sea levels, and increasing concentrations of greenhouse gases. Each of the last 3 decades has been successively warmer at the Earth's surface than any preceding decade since 1850. Of course, the warming effect due to human emission of greenhouse gases is derived from basic physical principles that were understood more than a century ago. The article clipping on the right is one such example of global climate change being mentioned by news media outlets over a century ago. The first known news article on the subject of climate change actually appeared as early as 1883. To understand how the IPCC has been able to make such a statement on human activity being the primary driver of climate change, it's important for us to enumerate all other possible drivers and eliminate them based on available evidence. There are, of course, many natural drivers that are potential candidates for affecting the Earth system on a wide scale. There are changes in solar forcing, changes in the amount of volcanic dust in the atmosphere, and internal variability of the coupled atmosphere-ocean system. This last category includes oscillations in the climate system, such as short timescale oscillations like the El Niño Southern Oscillation depicted here, through long timescale oscillations such as Milankovitch cycles that we learned about in Lecture 4. In addition to natural drivers, we've also learned about several ways human activity has impacted the Earth system. These include, firstly, changes in atmospheric concentrations of greenhouse gases through human emissions. Secondly, the addition of aerosols and particulates into the atmosphere, such as smoke from burning fossil fuels and biomass. Third, land use changes that impact the reflectivity or albedo of the Earth's surface. This figure, coming from the IPCC Fifth Assessment Report, provides a concise summary of the effects we have had on the amount of radiation received by the Earth's surface. Each row provides a measure of the change in radiation received by the surface, including combined solar and terrestrial radiation, from that factor, as quantified through observations and modeling of the Earth system. The change in radiative forcing is in watts per meter squared, analogous to insolation. On the right-hand side, we see numeric values corresponding to our confidence range, and the associated level of confidence in those values, from very high, denoted VH, to high, medium, and low. As more observations and theory are added to the mix, we are able to narrow the range of possible values for each row and increase our confidence. The first 4 rows are contributions from directly emitted greenhouse gases, including carbon dioxide, methane, halocarbons, and nitrous oxide. The most significant contributor to warming is carbon dioxide, responsible for about 1.68 watts per square meter of warming. This is followed by methane and its products at 0.97 watts per square meter, halocarbons, including CFCs, with 0.18 watts per square meter, and nitrous oxide with 0.17 watts per square meter. The next 3 rows are associated with short-lived gases that can undergo chemical reactions to produce greenhouse gases. These include carbon monoxide, a common product of wildfires, non-methane volatile organic compounds, or NMVOCs, and other nitrogen products. The last row is identified by the name NOx. It undergoes chemical reactions to produce nitrate aerosols and can remove methane from the atmosphere through chemical reactions. Hence, it generally has a cooling effect on the planet. The next 2 rows are related to aerosols, fine particulates much larger than individual gas molecules that can become suspended in the air. They include mineral dust, such as sand blown from the desert, sulfate aerosols, which are produced from coal power plants and volcanic eruptions, nitrate aerosols, which are a byproduct of agriculture, organic carbon and black carbon, which are natural byproducts of vegetation and also produced through biomass and fossil fuel burning. Most aerosols are highly reflective to incoming solar radiation and so have a cooling effect on the Earth. However, black carbon, produced through fossil fuel burning and wildfires, acts more like a blackbody, absorbing much of the incident radiation. The cloud adjustments due to aerosols reflect the fact that more aerosols in the atmosphere will tend to produce more clouds, which are highly reflective, as we'll talk about later in this class. There is substantial uncertainty on the effect this cloud adjustment has on total warming. The next row corresponds to changes in the Earth's albedo due to land use change. It is widely accepted that through human activities, including destruction of global forests, we have converted the dark forested surfaces into lighter cropland, driving up the albedo of the planet. In doing so, we have reduced the total radiative forcing and so have driven some cooling of the surface. The final row corresponds to the only natural mechanism we know of that has had a significant impact on total radiative forcing at the surface, namely solar irradiance. Solar output has increased very slightly since the 1750s, but we are confident that this effect is small, at most 0.1 watts per square meter. In total, as of the time of the production of this plot, namely 2011, we have high confidence that anthropogenic forcing relative to 1750 is around positive 2.29 watts per square meter at the surface. For comparison, recall that natural solar insolation is responsible for about 341 watts per square meter. As of today, in 2020, the total forcing from human activities is estimated to be around 3 watts per square meter. You may have noticed that this chart does not include forcing due to natural variability. As discussed earlier in the course, natural variability exists on a variety of timescales ranging from months to millennia. For example, volcanic eruptions have effects that last for years after. To date, we have quantified effectively all possible sources of natural variability that could occur on timescales of years to decades, and none of them have the timescale or magnitude of observed climate change. In particular, our climate models, the most comprehensive representation we have of the physical system, are only able to reproduce observed warming of the past 50 years if anthropogenic forcing or anthropogenic activities are included. By far, the most of the observed warming can be attributed to greenhouse gases through the greenhouse effect. Recall that the greenhouse effect refers to the trapping of terrestrial radiation by greenhouse gases in the atmosphere. This increases the radiative forcing in watts per square meter because more energy is radiated down to the surface from the atmosphere. These greenhouse gases then act as a blanket for the planet, keeping it much warmer than it would be if it had no atmosphere. Although there are natural levels of these greenhouse gases in the atmosphere that keep the surface inhabitable, there is indisputable evidence that through human activity we have had significant effects on the concentrations of these gases in the atmosphere. Greenhouse gases include water vapor, carbon dioxide, methane, nitrous oxide, and fluorinated gases. Water vapor is the strongest greenhouse gas, but is a natural part of the water cycle and so is quickly removed from the atmosphere when it is in excess. Carbon dioxide, on the other hand, is largely non-reactive and so can persist in the atmosphere from 50 to 200 years, depending on the removal process. It primarily comes from burning of fossil fuels, including coal, natural gas, and oil, solid waste, trees and wood products, and also as a result of certain chemical reactions, including manufacturing of cement. Carbon dioxide is primarily removed from the atmosphere or sequestered when it is absorbed by plants as part of the biological carbon cycle, through absorption into the ocean or through slower geological processes. In the US, about 81% of greenhouse gas emissions are in the form of carbon dioxide, out of 6,511 million metric tons of carbon dioxide equivalent emitted. Methane accounts for approximately 10% of total U.S. greenhouse gas emissions. Methane is emitted during the production and transport of coal, natural gas, and oil. Methane emissions are also result from livestock and other agricultural practices, and by the decay of organic waste in municipal solid waste landfills. Methane persists in the atmosphere for around 12 years after emission. Nitrous oxide represents the next most significant greenhouse gas emitted in the U.S. It is emitted during agricultural and industrial activities, as well as during combustion of fossil fuels and solid waste. Nitrous oxide persists in the atmosphere for around 114 years after emission. Fluorinated gases represent around 3% of total U.S. greenhouse gas emissions. These include hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride, and nitrogen trifluoride, and are synthetic, powerful greenhouse gases that are emitted from a variety of industrial processes. Because they are relatively non-reactive, they can persist in the atmosphere for hundreds or tens of thousands of years. Pound for pound, most fluorinated gases produce warming that is more than 10,000 times that of carbon dioxide. The contribution to warming from human activity has been steadily increasing over time as more of these greenhouse gases are dumped into the atmosphere. Between 1990 and 2018, there was a 43% increase in total warming because of anthropogenic greenhouse gases. The contributions to that warming came mostly from carbon dioxide, but there have also been significant contributions from methane, nitrous oxide, and the fluorinated gases. Through 2018, the heating imbalance has now reached over 3 watts per square meter, as mentioned earlier. Anthropogenically emitted carbon dioxide is the source of over 60% of the observed warming due to human activity. Thanks to the work of Charles Keeling, we also have very accurate measurements of atmospheric carbon dioxide since 1958 from Mauna Loa. This record again shows that atmospheric levels of carbon dioxide have increased substantially because of human activity, from 280 parts per million pre-industrial to around 410 parts per million today. Our historical records of CO2 concentration from ice cores reveal that these levels of CO2 are far above any other time in human history, or even the past 800,000 years. Prior to industrialization, CO2 levels had only reached 300 parts per million once, around 320,000 years ago. Over the Pleistocene, levels have oscillated naturally between around 180 to 280 parts per million. This video from NOAA shows the number of global measurements that are used for accounting of carbon dioxide. This graphic is known as the pump handle, since the seasonal oscillations of carbon dioxide due to vegetation growth cause carbon dioxide levels to oscillate over the course of a year, atop an indisputable upward trend. The left plot here shows variations in global CO2 across various latitudes of the globe, while the right shows the average trend at Mauna Loa and the South Pole. In October 1989, Mauna Loa saw 350 parts per million of carbon dioxide for the last time, as levels continued to rise. As we can see in the plot on the left, the oscillations are much more severe in the Northern Hemisphere. This is due to the majority of emissions coming from the Northern Hemisphere, as well as the majority of vegetation growth occurring in the Northern Hemisphere, along with most of the planet's landmass. Through 2000, levels continue to rise. Some of the first recorded measurements above 400 parts per million are now appearing on this plot. Around 2004, average carbon dioxide concentration was 380 parts per million. A variety of measurements have been used in order to construct this plot, including ship records as well as local stations. Having reached the end of the measurement period in 2014, we're now looking back using Keeling data, which extends back to 1958. This again represents the work of Charles Keeling, his measurements taken at Mauna Loa. To go back in time farther, we can use the Law Dome ice core in order to take carbon dioxide concentrations prior to industrialization. Here again we see carbon dioxide levels fairly stable around 280 parts per million. This chart is extended back further, again using ice core measurements. Here, the cyan line shows the Vostok ice core, and we see oscillations that bring us back into the last glacial maximum about 21,000 years ago, where carbon dioxide levels were around 180 parts per million. Going back farther, we see oscillations between glacial and interglacial periods, where again carbon dioxide levels move between 180 parts per million and around 280 parts per million. Nonetheless, through this whole record, we have not seen carbon dioxide levels that have reached the levels that we observe presently. If you want to view this animation again, check it out on YouTube at the link here. As we have already seen, there is strong evidence of the close relationship between carbon dioxide concentration and temperatures, as observed in ice cores taken over the past 800,000 years. High carbon dioxide levels naturally drive higher temperatures. Higher temperatures naturally lead to a loss of solubility in the oceans that then drive up atmospheric carbon dioxide levels. Carbon dioxide is relatively well mixed globally, meaning that the concentration doesn't vary too much depending on location. Natural weather patterns carry carbon dioxide globally from their points of emission, although over shorter time frames most carbon dioxide remains in the hemisphere of its emission. This video from NASA, narrated by Bill Putman, shows how our climate models are able to simulate global weather patterns that carry carbon dioxide and carbon monoxide around the world. The resulting warming from greenhouse gas emissions over the past century has been unambiguous. Over the past century, warming of roughly 1 degree Celsius or 1.8 degrees Fahrenheit are apparent over the 140-year surface temperature record. Atop this trend is still evidence of natural variability, including major El Niño episodes associated with high temperatures, major La Niña events associated with low temperatures, volcanic emissions that drove down temperatures over the course of several years, and other longer-term oscillations. This evidence of warming is backed up with multiple lines of evidence. Temperatures over land and air temperature near the surface has been increasing. Specific humidity, a reflection of water vapor content in the atmosphere, has also been steadily increasing. Independently observed oceanic indicators similarly show a clear signal of change. Ocean heat content has been increasing, as oceans are increasingly acting as a battery for surplus energy. Sea level has been steadily increasing as thermal expansion and land ice melt drive up ocean levels. Sea surface temperature and temperature over oceans have both been steadily increasing as well. Oceanic heat content has been generally confined to the near-surface ocean above 700 meters depth. This is due to the slow circulation of oceanic waters and the relative disconnect between the oceanic surface and ocean at depth. Nonetheless, there has been a steady diffusion of heat from the surface to depth, and new estimates suggest the deep ocean is increasingly acting as a buffer against climate change by storing built-up energy. The cryosphere has been similarly seeing dramatic decline. Although it takes thousands of years to build up glaciers, we've seen rapid decline in glacial mass over just the past several decades. Global snow cover is similarly dropping, with increasingly less area covered by snow. Finally, as you've likely heard, sea ice extent in the Arctic region has been experiencing steady decline, with observations of decline actually outpacing those of our climate models. Everything we've talked about to date in this lecture has reflected historical observations of change. However, using climate models and a physical understanding of the Earth system, we can project the future as well. This has been done through a global effort known as the Coupled Model Intercomparison Project. CMIP, as it's abbreviated, is a global scientific effort where modeling centers worldwide perform a uniform set of experiments to predict future change. We'll discuss this more in later classes. These experiments have a consistent design to ensure that uncertainties can be quantified based on how different models react to the change. Future scenarios are first constructed by consulting with economists and sociologists to build socioeconomic scenarios. That is, measures of population growth, industrial activity, and energy demand. Then, by estimating how much energy is generated, whether through fossil fuels or renewables, we can construct emission scenarios that enable us to estimate future atmospheric greenhouse gas concentrations. These greenhouse gas concentrations subsequently allow us to estimate radiative forcing, how the pathways for energy will change within the atmosphere. 4 such scenarios were constructed for the 5th assessment report, known as Representative Concentration Pathways, or RCPs. These scenarios are named based on the amount of radiative forcing predicted by 2100. Perhaps the most well-known of these is the so-called business-as-usual RCP 8.5 scenario, which assumes historical fossil fuel burning will continue to meet growing energy demand. It is shown in the red curve on this plot and reflects a CO2 concentration of nearly 1250 parts per million by the end of the century. Note that this value, 8.5, corresponds to the value 3.0 of radiative forcing that we experience at present. On the other end of the scale is RCP 2.6, which reflects aggressive policy action and technological development focused at reducing carbon dioxide output, along with eventually developing the technology for removing carbon dioxide from the atmosphere. 2 other middle-of-the-road scenarios were also developed, known as RCP 4.5 and RCP 6.0. With these RCPs in hand, operational centers worldwide can contribute the results of their Earth system model simulations to a global dataset of future projections. With these in hand, we can then obtain estimates of future changes in temperature under each scenario. By 2100 under RCP 8.5, we see global temperatures 3 to 5 degrees Celsius higher than observed 2005 temperatures. This is in contrast with a 1 to 2 degrees Celsius increase under RCP 2.6. Several of the models that were run out to 2100 carried their run on farther to 2300 under the assumption of stabilized CO2 concentrations. Even after 2100, we see a steady increase in temperatures under RCP 8.5, reaching a range more analogous to the historically warm Eocene epoch by 2300, around 8 degrees Celsius warmer than present. In the 6th assessment report, these RCPs were revisited in light of associated socioeconomic challenges for adaptation and mitigation. These included 5 shared socioeconomic pathways, or SSPs, which reflect differences in regional policy and land use change. We'll revisit these shared socioeconomic pathways later on, but by definition, these are scenarios of projected socioeconomic global change up to 2100. They've been developed for the IPCC 6th assessment report and incorporate both greenhouse gas emissions as well as different climate policies. Climate models in theory give us far more than just temperature increases. They can tell us about anticipated changes to the Earth system, which are a consequence of these temperature changes. In terms of temperature, as we already noted, we anticipate over the next 2 decades a global rise of 0.2 degrees Celsius in global temperatures. Global average rise is anticipated to be between 1.8 degrees Celsius, or 3.2 degree Fahrenheit, and 4.0 degrees Celsius, or 7.2 degree Fahrenheit by end of century, depending on the emission scenario. Temperatures over land are expected to increase faster than temperatures over the ocean, and increases is expected to be larger at higher altitudes due to what is known as elevation-dependent warming, as well as in polar regions. Because of these changes in temperature, we anticipate changes in precipitation as well. Again, we're following this basic rule of thumb. Dry becomes drier, wet becomes wetter. Increased temperatures will cause increased evaporation, leading to more water vapor in the air, on the order of 7% per degree Celsius, as well as causing a speed up in the global water cycle. Expansion of Hadley cells, as we'll talk about later in the class when we talk about the general circulation, may occur, leading to an intensified storm track and more desertification, that is, conversion of the world's biomes to deserts. Global average precipitation will increase about 3 to 5%, but the actual change in precipitation is highly dependent on region. For instance, California is anticipated to receive an increase in precipitation, but much of the U.S. Southwest is expected to become drier. In the cryosphere, we anticipate accelerated melting of all aspects of the cryosphere to occur, including snowpack, sea ice, and glaciers. As well, warmer temperatures are driving sea levels up via thermal expansion of the ocean and melt of land ice. During the 20th century, sea level already rose about 10 to 20 centimeters, or 4 to 8 inches. Thermal expansion and ice melt each contributed about 50% to this rise. By 2100, the rise is anticipated to be between 20 and 50 centimeters, or 8 to 20 inches above 2000 levels. Over this period, thermal expansion will contribute about 75% to this rise. As well, we're anticipating acidification of the oceans due to higher carbon dioxide concentrations. When carbon dioxide is dissolved in the oceans, it produces carbonic acid. This is thought to have reduced the ocean pH by about 0.1 since pre-industrial. Further acidification of about 0.14 to 0.35 pH is expected by the year 2100. Finally, extreme weather is anticipated to become more extreme. Tropical cyclones, extratropical cyclones, and atmospheric rivers will be impacted by increased temperatures. Warmer oceans will cause intensification of these storms. However, the frequency of tropical cyclones and extratropical cyclones may decrease. Okay, that covers our introduction to global warming and climate change. Where do you see yourself being the most affected by climate change? And on the flip side of the coin, where do you see yourself contributing to the fight against climate change? In the next 2 lectures, we'll wrap up this section of the course with a discussion of aerosols and of the ozone layer. In the ozone layer, I hope to give you some optimism. It was a challenge that was faced by humankind and one that we have largely overcome. Talk to you next time.